Alaikum. Photon is a particle.
So how do we reconcile the two concepts of the wave and the particle? But first of all, we'll have to see that the photon indeed does carry momentum. So the experiments that we've seen so far, namely the photoelectric effect, as well as the emission of X-rays, they do not tell us anything about the momentum of the photon. Alright? And there is a basic difference between energy and momentum. First of all, they are different quantities, they have different dimensions, but energy is a scalar, whereas momentum is a vector. So there is a certain direction associated with a momentum. And there was one homework example in which you were asked to look at an atom, and in an atom the energy levels are quantized, and an electron makes a downwards transition and it emits a photon with a particular energy Hn. And the question asked you whether this atom will move. As it emits a photon, will it move? If I have a ball in my hand and I would like to throw it, and I would like to throw it very far, I will take a backward push. So, because the ball will have a momentum as it is issued out of my hand. Likewise, this atom is emitting a photon. Now this photon is being emitted in a particular direction, say towards the right. This photon is carrying away some momentum, and that momentum is given by P. So the momentum will be equal to HF over C. In दोनों को equate करें, you can find what the momentum is. In other words, the momentum is going to be H over lambda. Now this momentum has a particular direction. It is towards the right. But momentum has to be conserved. Before the emission of the photons, the total system had zero momentum. It was at rest. So the atom should take a backwards kick in order to preserve the momentum. So this atom as a whole will move backwards with a certain velocity, say capital V. And this momentum, mv, where m is the mass of the atom, it's not the mass of the electron, it's the total mass of the atom, will be the velocity will adjust itself such that this mv equals h over lambda. Alright? However, the problem is that since the mass is very large of the atom as compared to an electron, this velocity is going to be imperceptibly small. Imperceptible का मतलब आपको नजर ही नहीं आएगा, इतनी छोटी velocity होगी, because this mass is very large. On the scale of an electron and an atom, the atom has a very large mass. if the atom is a hydrogen atom, it's a proton and an electron. A proton is about 10,000 times heavier than an electron. So this velocity of the atom will be very small, and it's very difficult to detect this kickback of the atom. However, this technique is used to cool atoms. Now this is an A side. I did not intend to tell you about this, but it just comes to my mind that if you have an atom that is moving in a certain direction, a velocity v. Now if the temperature of this atom is high, what can you tell about the velocity of the atom? It's going to be high. And could you tell me what, if the temperature is T and the temperature is doubled, what's going to happen to the velocity? Will it double? It's going to be 4 times. V square, which is the energy, is directly proportional to the temperature. So you increase the temperature, the velocity goes up by 1 over under root 2, which means that the velocity is proportional to the square root of temperature. So if the temperature doubles, the velocity is multiplied by under root 2. It's multiplied by 1.4. It goes up, increases by about 150 or 140%. Where does this relationship come from? This is just half mv squared, which is the kinetic energy of the atom, and that's proportional to k times T, where k is the Boltzmann constant. So now, higher the temperature, higher will this velocity be. Now if you would like to cool an atom, if you have an atom and you would like to cool it, which means you would like to lower the temperature of the atom, which means you would like to lower the velocity of the atom, what they do is they have a laser beam which is issuing photons, and they are moving in a particular direction, and the direction is such that it's against the velocity of the atom. So this photon will transfer its momentum to the atom, and the velocity of this atom will, as a result, decrease. Because this momentum is pointing in the left direction, this momentum is pointing in the right direction. So this atom will observe a viscous force, an impeding force from the photon, because it is carrying momentum. ठीक है, एक लोगों की भीड़ है और बहुत से लोग मेरी तरफ चलते हुए आ रहे हैं. There's a large number of people walking this way. If I try as a lone atom try to walk against the direction of the traffic, I'll face resistance. This is what is happening to the atom. It is trying to move in a direction such that it's against the momentum of the photons that are hitting it. And there are a large number of photons coming out from the laser. Okay. So as a result of these photons and the momentum carried by the photons, this atom will come to a rest, or it will decelerate. Its velocity will decrease. But who is telling the atom to move in the right direction? If the temperature is high, the motion of this atom is totally random. So it can move in the right direction, but it can also move in the left direction. So you shine another laser beam in the opposite direction. But this atom can move in the upward direction or the downward direction, because the motion of the atom is totally random. So this atom can move up, it can move down. So you have to shine laser beams from the top and the bottom directions as well. G. Yes. It does. So now you have an atom that is trapped on all sides from laser beams. This is called an atom trap. And inside the atom trap, the atom will be cooled because its velocity is going to decrease. And you can hold an atom static at a particular point in space by shining laser light on it. So lasers are very strange in that respect. This technique was awarded with the Nobel Prize. This is called laser cooling. Now lasers are very strange because with the help of lasers you can achieve the fusion reaction and demonstrate temperatures of the order of 4000, 3000 kelvins. So you can achieve very high temperatures. And with the help of lasers you can also achieve ultra low temperatures of the order of microkelvins, that is 10 raised to power minus 6 kelvins. So you are achieving temperatures of the order of 10 raised to power 4 kelvins with the help of lasers and 10 raised to power minus 6 kelvins with the help of lasers. These are 10 orders of magnitude. So just with lasers you can achieve the hottest temperatures possible on Earth and the coldest temperatures possible on Earth. And it looks very strange because if you shine laser on an object, it tends to increase its thermal energy. But now with the help of lasers, we are actually cooling atoms. So all of this shows that the photon does carry a momentum. And there was one experiment that was performed in 1922 by a British physicist, Compton, that presented a convincing proof that the photon does indeed carry momentum. Now, any questions up to this for this experiment? All right. G. The temperature is lowered, which means that the movement of the atom is restricted. Previously, it was moving with higher velocities, and since it was moving with higher velocities, it would travel, it would jitter by a larger amount. Jittering means it just moves around, it jostles. But now you're shining light on it from all directions. So its motion is restricted, which means its velocity is restricted, which means it remains at a fixed point, so more or less, and its jitter is reduced. And the temperature is reduced as a result, because the temperature is nothing but the average kinetic energy. Now what the Compton effect looks like, it was one of the most beautiful experiments, the landmark experiments in all of physics. Now how did the Compton effect work? Suppose you have a photon. आपको मेरी आवाज ठीक कर रही है? Suppose you have a photon, like always I am showing it with a wavy line. Now this photon has an energy hf and it carries some momentum, let's call it P naught. Have you studied the Compton effect before in your A levels? No. Is it in the A levels course? The video is being made, but sorry, mic is not. बैटरी ठीक है, बगैर इसके
दूसरे माइक से कर रहा हूँ।
ये चल रहा है, पक्की बात है। अच्छा, कल की वीडियो किसी टेक्निकल फॉल्ट की वजह से अवेलेबल नहीं हो सकती, जो गुजरा कर ले, गुज़श्ता कर ले। अच्छा, ये एक फोटोन है, it's coming in, it's carrying some energy and some momentum, and it sees an electron. देखो मैं बहुत अनड्यू लिबर्टी ले रहा हूँ, मैं इलेक्ट्रॉन को भी एक स्फीयर से जाहिर कर रहा हूँ, मैं एक फोटोन को भी एक स्फीयर एक पार्टिकल से जाहिर कर रहा हूँ। मिड टर्म के बाद बताऊंगा ये मैंने बहुत ज्यादा अनड्यू लिबर्टी ले ली है पार्टिकल्स को इस तरह दिखाने की। लेकिन this is something commonsensical that we all tend to think what an electron is, what a photon is. Now this electron is at rest. Now what happens, and this electron is not inside an atom. It's not bound to a nucleus. It could be inside inside a metal or inside a solid, but it's not bound to the nucleus. Alright? So it does not have a neighboring energy level to which it can make a transition. Now what happens is that this photon is scattered, which means it goes out in a certain direction, and this photon carries an energy F dash. Now this F dash has to be different from F, and it carries a momentum. Let's call that momentum P. And this electron, as a result of this collision between the electron and the photon, also scatters. It also takes a kick. It also takes a push. Suppose it goes in this direction. And it has a kinetic energy as a result of the collision. Let's call that kinetic energy K. And let's call its momentum P1. Now we have to analyze this problem. We are treating this problem as a collision between two particles, and those particles after the collision they are moving in different directions. This is the undeflected or the path of the undeflected photon. Let's call this angle theta, and let's call this angle phi. Now energy has to be conserved and momentum has to be conserved. And remember that this process is an elastic process. It does not cause any change in the internal energy of the substance in which the electron is present, because this electron is not being promoted to a higher level, or it is not being ionized. It's just being scattered. Now if you look at energy conservation, this energy HF plus the energy of the electron before the collision has to be equal to the energy of the electron after the collision plus the energy carried by the photon after the scattering process. Typically this is an X-ray. Typically. Now I would like to tell you something about energies. One is the energy of being. ठीक है? अफलातून ने कहा था मन आनम के मन दानम, I know therefore I am. अगर कहे मन आनम के मन हस्तम, I am because I exist. I have energy because I exist. So this is the energy due to the being of a particle. It's just present. So if a particle is at rest, it still has energy, because you can convert that mass into energy. So there has to be some intrinsic energy inside the mass of an object. This was Einstein's proposition, and it is given by the famous relationship E equals mc squared. This is probably the most famous equation of physics. फिजिक्स की इक्वेशंस की दुनिया में सबसे ज्यादा लोग होंगे फिजिक्स की दुनिया से बाहर जो इस इक्वेशन को जानते हैं, F equals ma से भी ज्यादा, ठीक है, क्योंकि पॉपुलर इक्वेशन है। ये इक्वेशन क्या बताती है कि एक ऑब्जेक्ट जिसका मास है m, that is equivalent to having a mass equal to E over c square. Or that mass can convert into energy easily, and energy can go back into mass. So the law of conservation of mass and the law of conservation of energy, they are special forms of the law of conservation of mass plus energy. Mass and energy are interconvertible, right? So this is the energy of being. So if I have an object of rest mass m naught, then its energy is equal to m naught c square, just even if it were at rest, even if it were not in a potential field, even if an electron was in vacuum, away from all stars, all planets, not seeing any gravitational attraction, it will have this much energy. Alright? So what about a photon? What's the rest mass of a photon? 0. So the rest mass energy of a photon is 0. Now what I would like to do, I would like to draw a triangle. And this vector is a horizontal vector. I like to call the length of this vector m naught c squared. It's the rest mass energy. And then I draw another vector which is vertical. And I call the length of this vector, I define it to be Pc. P is the momentum of a particle and C is the speed of light. So it could be an electron, it could be a proton. You take the momentum of the electron or the proton or the photon and multiply it with the speed of light. So this picture is not valid just for a photon, it's valid for any particle. Okay? And this is a right angle. Now if I draw the hypotenuse, then this energy, this length of the hypotenuse will give me the total energy of this particle. So the total energy of the particle E, any particle, it could be a photon, it could be an electron, it could be anything, it could be me, anything is given by the length of this hypotenuse. It's m naught c squared plus pc squared, right? Now for a photon, this term is 0. So the energy is just Pc. Okay? So this is valid for a photon as well, this picture. For an electron, there will be some rest mass. How will you find the rest mass of energy? If an electron disappears, if an electron is in vacuum, it suddenly fizzles out, it disappears. It will convert into energy. So how much energy will it convert into? That will tell us what the rest mass of the electron is. Alright? So this is the energy of any particle. Another thing that I could do is, I could draw an arc with this as the center of curvature. Now what is this length going to be? M naught c squared. This is just the rest mass energy. Now, if this were to be the total energy is the sum of the rest mass energy and something that is left over. And what is that left over going to be? The kinetic energy, shabash. This is the kinetic energy. So there are two ways of defining the energy. The energy can be defined as m naught c squared, which is the rest mass energy plus the kinetic energy, and it's also equal to m naught c squared plus pc squared under root. Okay? So this is a relativistic expression for the energy. This energy is called the relativistic energy. देखो एनर्जी के दो कंपोनेंट्स है किसी भी पार्टिकल की, एक रेस्ट मास एनर्जी होगी और बाकी सारी की सब एनर्जी वो काइनेटिक एनर्जी होगी, ठीक है। सो द एनर्जी इज द सम ऑफ दिस एनर्जी एंड द काइनेटिक एनर्जी, but it's also equal to the length of this hypotenuse. So both of these expressions have to be equal. So for a photon, all the energy is kinetic because this is 0, and that kinetic energy equals Pc because this is 0. G. So this comes out, this expression, this one comes out of special relativity. That's slightly beyond the scope of this class. But this is a useful mnemonic. Mnemonic समझे? याद रखने का तरीका। Now let's look at the Compton experiment. Could you write the energy conservation expression, please? थोड़ी सी आवाज क्या? वो तो फुल है उससे ऊपर तो उनकी बोलनी पड़े, थोड़ी सी बेहतर हुई, थोड़ी सी मजीद तो ठीक है। अभी जरा देखो इसमें रेस्ट मास का है, क्यों? इलेक्ट्रॉन का रेस्ट मास 0 तो नहीं है। इलेक्ट्रॉन का रेस्ट मास इलेक्ट्रॉन का रेस्ट मास भी तो है, कैंसिल हो जाएगा, लेकिन लिखो जरूर, ठीक है, ठीक है। एनर्जी के कोई कॉम्पोनेंट, एनर्जी तो एनर्जी है, एनर्जी के कोई कंपोनेंट्स नहीं होते। ये दिस इज द एनर्जी along the x axis, this does not make sense. एनर्जी को आप रिजॉल्व नहीं कर सकते कंपोनेंट्स में कि व्हाट्स द एनर्जी along x axis, फोर्स को कर सकते हैं जी। Energy conservation tells us that HF plus m naught c squared, which is the rest mass of an electron, plus 0, which is the kinetic energy of the electron, has to be equal to HF dash plus, there's still an electron still exists, so m naught c squared plus the kinetic energy of the electron. This cancels out, so we have HF is HF dash plus K, and we can also write this as PC equals P naught C equals PC plus K, or K equals P naught minus P over C. This is the energy conservation equation. Now can you please write the momentum conservation equation? थीटा फाई के बराबर नहीं है। हाँ, तो थीटा फाई के बराबर तो नहीं है ना। देखो अब इस ये मोमेंटम एक वेक्टर है, इसके कंपोनेंट्स होंगे। आपने मोमेंटम को एक्स डायरेक्शन में भी कंजर्व करना है, वर्टिकल डायरेक्शन में भी कंजर्व करना है। K और P1 तो P नॉट इस मूवमेंट So in the x direction we have the momentum of the photon is p naught and all of it is in the x direction. And what's the momentum of the electron? 0, because it is at rest. There is no consideration of the rest. There is no such thing as rest momentum. Alright, so P naught must equal the components of the momenta of the electron and the photon of scattering along the x direction. So it has to be equal to P1 cosine of phi plus P cosine of theta. And for the vertical components we have P1 sine of theta equals P sine of P1 sine of phi equals P sine of theta. Not minus. This minus this equals 0. Now what I would like to do, I would like to see how the wavelength of the photon changes, how the frequency of the photon changes. This is my intention. So I would like to eliminate the effect of the electron which from the equations. Okay? So what I can do, I can write the first equation as P naught minus P cosine theta equals P1 cosine of phi. I can square this and add it to this, to the square of this. So I get P1 squared cosine squared phi plus P1 squared sine squared phi is P squared sine squared theta plus the square of that term, which is P naught squared plus P squared cosine squared theta plus 2 P naught P cosine of theta. So this becomes P1 squared minus it. So this becomes equal to P1 squared equals P squared plus P naught squared minus 2 P naught P cosine of theta. Let's call this equation 2 and let's call this equation 1. So we've eliminated the angle phi. Now there is no phi inside this equation or that equation. Now let's look at the electron. If I consider the electron, the energy of the electron, E electron, is given by what's the energy of the electron? M naught C squared plus the kinetic energy, correct? This one. And this is also equal to this. So M naught C squared, I am writing the square of the energy. I write a square here. This equals M naught C squared plus what's the momentum of the electron? P1. P1 C squared. Alright? So I expand out these terms. I get M naught C squared plus K squared plus 2K M naught C squared equals M naught C squared plus P1C squared. This cancels out. Okay. So I'm left with K squared plus 2K M naught C squared equals P1 squared C squared. So let's divide both sides by C squared. Get K over C squared plus 2K M naught equals P1 squared. So now I would like to get rid of the K's because that is giving me some property of the electron. I would like to focus on the photon only. So what I would do, I would take K from equation 1. K over C is in fact P naught minus P from 1. देखिए मैं सिर्फ एक लेबिरिंथ में फंस गया हूँ और कुछ नहीं हुआ, लेकिन this is something that I have to go through in order to derive a beautiful result. अब कभी दुश्वार गुजार रास्ते से होके बड़ा खूबसूरत एक मंजर आता है. This is what we are aiming at. So let's write K over C. K over C equals P naught minus P from equation 1. P naught minus P squared plus 2. Now what is K? K is again P naught minus P times C. M naught equals P1 squared. So this becomes P naught squared plus P squared minus 2 P naught P plus 2 M naught C P naught minus P equals P1 squared. But what is P1 squared? P1 squared from equation 2 is given by this. So this equals P squared plus P naught squared minus 2 P naught cosine of theta. So the P naught squared cancels out, the P squared cancels out, and I am left with something very nice and attractive looking. So what I can do, I can cancel out the 2's. I can write P naught minus P equals, this goes to the other side, P naught P minus P naught P cosine theta. और चूंकि अब मैं इसको थोड़ा सा ऊपर लिखता हूं आपको नजर आए, this becomes P naught minus P equals P naught P, there's also an M naught C here, M naught C 1 minus cosine theta. I would like to divide both sides by P naught P. Now can you write this in terms of the wavelengths of the photons, please? Lambda minus lambda naught is h over m naught c 1 minus cosine of theta, where lambda is this wavelength, lambda naught is this wavelength, and lambda is this wavelength. So what's happening to the wavelength? Is it increasing or decreasing? The wavelength is increasing, right? If this cosine theta is less than 1. It's between 0 and 1. And even if it goes up to pi, this will be 1 minus minus 1, which is 2. So now let's look at this equation, and what does this equation mean? And then we'll stop and then we'll continue after the midterm. Now this was Compton's result. What this result shows is that the change in wavelength, this is the wavelength of the incident photon and this is the wavelength of the scattered photon. It depends upon fundamental constants h, m0 and c, and depends upon the scattering angle. So what's going to happen in an experiment is that you have an electron and you shine photons on the electron. So this is a photon, HF, and you shine photons on the electron. So there will be some photons emitted at a certain angle θ1. In another experiment, a photon may be emitted or scattered at an angle θ2. So photons are being emitted at all angles, θ1, θ2, θ3 and so on. And each of these photons will have a precise wavelength. And that wavelength is given by lambda naught plus h over m naught c 1 minus cosine theta. And each of these wavelengths, this will be at a different wavelength because the scattering angle is different. Theta has changed. This will be at a different wavelength. The scattering angle has changed. In each of these processes, the scattering angle of the electron will also change because momentum has to be conserved and not. But right now we are focusing our attention on just the photon. How does the wavelength of the photon change? So what we're going to do is we're going to carry this discussion forward after the midterm, and then we're going to look at what really is matter. Can matter also act like a wave? For example, can an electron act like a wave? So far we've seen that photons act like particles and waves at the same time. But what about electrons? And that is the most surprising element of quantum mechanics. And then we'll go into the realm of Schrödinger mechanics or quantum mechanics. So I wish you best of luck for tomorrow's test. It's going to be a very conceptual exam. It's just going to be 2 hours. There will be no problem of time whatsoever. I wish you best of luck. There are going to be multiple choice questions. There are going to be short questions and a couple of slightly longer questions.